The basic goal in cryptography is to send a message in a way that only the intended person can understand it. Now, this is a very old problem. Long before computers, people needed to protect military orders, diplomatic messages, and secret communications. And so, one famous historical example was with Julius Caesar. And so, he used a simple method to encrypt military messages. It is not secure by modern standards, but it is a good starting point for like looking at cryptography and how something like this can be done. So let's take a look. So Caesar's cipher is an example of something called a shift cipher, and the idea is quite simple. So every letter is shifted forward by the same fixed number of positions. So for example, if we consider a shift by 3 positions, then if you want to send the plain text is the text itself that you want to send, and the ciphertext is what you are sort of encrypting it into. What you do is you take every letter in the plain text and you shift it 3 letters forward. So it's A, B, C, D. So A becomes a D, T becomes a W. You see the A here becomes this D, the C becomes an F, and so on. And decryption is quite simple. You just need to know by how much the person shifted, and you just shift backwards, right? So if you take this and you know that the original thing was shifted 3 back, you just do that to get your answer. So the key idea is that both the sender and the receiver need to know the shift amount. And so that shift amount is what we call like the secret key. It's the thing that if you know, you're able to decipher. So let's write the shift cipher using modular arithmetic, right? So of course we were doing it with letters, but you can there's an arithmetic way of looking at it, and it's gonna end up that it's something that's related to the congruences we've been seeing in the course. So first we assign numbers to each letter. So let's say we assign A the number 0, B the number 1, and so on up to Z being 25. So we have 26 numbers. And so what we'll do is we're gonna work modulo 26. Because if you see what we were talking about here, what happens if you want to shift a letter Z? You go around the alphabet. So it's exactly what the modulo's done. So you can think of the letters in a clock, right? And so you're doing clock arithmetic. So if P is the plaintext letter as a number, and K is the key, which in the previous example was 3, the way you encrypt, so this is the encryption that depends on the key of the plaintext P, is you add K to the plaintext mod 26. And then decryption is just the opposite. You subtract K, and of course, if you decrypt an encryption, so if you add K and then you subtract K, you get the original message back, right? And so this wraparound behavior from the arithmetic is exactly what we want. When you go to 25, you wrap around to 0, right, and continue from there, which is the same as saying that when you go to Z, if you add 1, you're back at A, which again is the clock arithmetic. So you make a clock and you put the letters in the clock. So let's see an example of this. So let's say that the secret key, so your plaintext message is hello, your secret key is K equal to 3. So what you do is you first transform the message hello into the numbers that correspond to it. You then add 3, and you can then reinterpret this as letters again. And so this is your ciphertext. And so hello gets encrypted into KHOOR. And if someone receives this and they know the secret key, they can just subtract 3 from these to obtain these numbers, which they can interpret as the message.